we stay with tensor networks. Please, John, proceed with the floor.
Thank you for the introduction, and a big thank you, of course, to the organizers for putting together this very nice program. So today I would like to talk to you about preparing states on quantum computers, and in particular, the focus will be on preparing states that satisfy entanglement area law, which is a very physical requirement. I hope many of you care about this. And these states are exactly captured well by tensor networks, and that's the title of my talk. So, okay, let's begin. I don't want to assume all of you are tensor networks experts, though many of you are. So I will try to avoid like talking explicitly about tensor networks, and hopefully I will make the talk more accessible. Okay, so what is state preparation? What is the task I want to consider? Suppose you have the classical description on a piece of paper of a quantum state, and you want to transfer this to a quantum device. How do you do this? You need to infer, given the classical description, what is the sequence of elementary operations that needs to be performed on the quantum device. In other words, state preparation for this talk is the algorithm that takes as input the description of the states and outputs the sequence of operations that create the state, and in particular, the formalism I will use will be that of a quantum circuit. Okay, good. So why should you care about this? So why do you want to prepare a state you already know? There are many good reasons, so I list some of my favorite here. The first one is quantum computing. If you have some experience with quantum algorithms, you know very often you need to have ancilla qubits and you need to prepare them in some state, like a GHZ state. So you should be able to do this. Also for quantum computing, you want to do error correction, then you need to prepare states like the toric code or other states that have nice properties and are tolerant to errors. And maybe variational algorithms is another class that goes in quantum computing. More physically, there is quantum simulation, and then we want to understand physical properties of a state by preparing on a device. So the first task, the key task, is to prepare some interesting initial states. So you need to know how to do this. However, this is more the practical motivation. There is a more fundamental motivation, which comes from quantum complexity theory. And this is if you understand how to prepare a state, and in fact, you can even put lower bounds on the preparation procedure, that means you understand something about the complexity of states. And that to me is very intriguing, because area law states that I will come to next are very relevant in many body physics, and understanding their complexity, hopefully you learn something about physics itself. Okay. So if one tries to solve this problem in full generality, that's impossible, right? And that's there's a very simple argument why, even if you count the number of states in a many-body Hilbert space, they're exponentially many. So you can't expect to prepare all of them efficiently. That's why I want to take some practical to restrict the set of states, and that will be practically motivated. And the first motivation is that current devices are noisy, and thus evolutions that can be implemented are short. So that's the first one. And the second one is that very often in practice, there are locality constraints. So not all qubits talk to every other qubit, but nearest neighbor talk to each other. And as I will show next, these two very naturally lead to consider tensor network states or area law states. Okay, so what's the outline? Maybe it's a bit ambitious. Okay, so the first part is I will tell you about this work we did together with people from MPQ, Daniel Maltz and Ji-Young Wei, and also Ignacio Sirac. And the idea is I'll show you an algorithm that will prepare all matrix product states and then tell you about its efficiency and the cost of the algorithm. So that will be the main part of my talk. And then that will very naturally motivate to look at another set of states, which I will justify later, which will be W and Dickey states. And this was work done with Lorenzo Piroli that came up also in previous talks, and also Ignacio. The third part I will also briefly pass is how one can view state preparation from a totally different lens, the lens of condensed matter, which is of classifying phases of matter, and their symmetries play a role. So I will introduce symmetry in the game. And lastly, if there is time, I will talk about more than one dimensions. Okay, so I should say questions are very welcome during the talk. So if you interrupt me and I don't make it to the end, I consider this a success. So please feel free to ask me. Good. So if everything is clear so far, let's start with matrix product states. So I will introduce what is this class and why it's relevant. Okay, so let's recall some basic facts. Hopefully everyone knows these things. First of all, we know short-time evolutions can be well approximated by shallow circuits. And this has many implications, which can be very easily read out of this picture. The first one is that the output states of short-depth circuits, of shallow circuits, have very limited entanglement. Namely, if you make a cut in the middle or somewhere on the system, you cannot have more entanglement than the number of layers, which is called depth in this context. So this is very well known, but however, there is a second one, which will be very important for this talk, which has to do with correlations. So it's not only entanglement that is limited, but in fact, there's a light cone structure on the correlations, which means if you pick, let's say, 2 qubits in the middle, then every layer can correlate the output state, but only to the nearest neighbors, no more than that. And the way to make this intuition very precise is to just take 2 regions A and B, and what this argument tells you is that if these 2 regions A and B are more than twice the depth far apart, then the state is necessarily a product. So again, it's not only low entanglement, but is the geometric locality brings in picture the fact that if you're far away, then your state is product. Okay, but at the same time, we know there are other interesting physical states that don't have this feature. For instance, we're all aware of GHZ states, which have little entanglement, but is long range. So in that sense, doesn't belong in this class. And otherwise, for instance, in one-dimensional systems, if you are interested in ground states of local Hamiltonians, these states have exponential decaying correlations, so they clearly violate the exact light cone. So this motivates very naturally to look at preparing not every state, but instead states in one dimension which have an entanglement area law. And this is nothing else than matrix product states. So if you're not familiar with this terminology, don't worry. Just whenever I say this buzzword, MPS or matrix product state, you should think of area law states in 1D. But more formally, there is a way to define this class of states just through tripartite tensors. Here I quote the formula if you haven't seen it before. But the point is, again, these states, whenever you make a bipartition, have entanglement which is bounded by a constant. This is the capital D, is called bond dimension. And throughout this talk, this won't depend on the system size. So I will consider making bigger and bigger matrix product states, but with constant bond dimension. Good. Okay, so what are the questions now that I have set up the scene? So the first thing I want to do is ask, are there fundamental limits on preparing matrix product states? So that means, can you prepare them how fast can you prepare them? What is the best you can do? And then I'll show you rigorous results. I won't justify very much in the interest of time, but that's a rigorous result, which we show that if they have short range entanglement, the depth of the circuit to create these states needs to be logarithmic in the system size. So that's the first thing I will talk about. And the second thing I want to consider is I want to actually break this bound. And the way to do this is to consider some extra resources. And extra resources here would mean that I go beyond the framework of only considering quantum circuits, and I want to consider other ingredients. And these are measurements and feed forward. So by these words, I mean what you know from quantum teleportation. For instance, there are 2 parties, Alice and Bob. They share some entanglement, they make measurements, and they correct based on the measurement outcomes. So these are exactly the same ingredients I consider here. And I will show you, if you allow on top of the circuits, this measurement and feedback, you can prepare the states much, much faster. So you gain an exponential speed up. So you go to double long. Okay, so that's the plan to explain these results in more detail for the first part. So let's start with the short range entangled states. Okay, so there are 2 kinds of MPS that will be relevant for this talk. The first one are long range entangled. They go by this term non-injective, but don't worry about this. The important thing is there is a standard representative in this class. That's the GHZ state. So this is long range, has correlation at every length scale. And there is a second kind at the bottom, this short range entangled. And standard representative here, except of course product states, would be AKLT state or cluster state, which maybe you have seen before. And these have exponentially decaying correlation. Great, so how can you prepare them? What are the limits? Now let's separate these two cases. If you go to long range correlated states, you necessarily need linear depth, and this was something known from mid-2000s. And moreover, this is optimal. And here the optimality is very easy to derive. It just comes from the fact correlations are at every distance. So you need this linear kind of depth to prepare them. Okay, so this is kind of trivial. Now, what about short range entangled state? Can you do better? And this is exactly what I will show you. You can do better. And as I announced previously, logarithmic depth is not only sufficient, but is also necessary. And that's the non-trivial part. So I will skip the part to justify whether that's optimal. I will only show you how it looks like. Okay, so this is the theorem, if you wish. So you consider some tensor and you repeat it n times. Now you get a state and you want to reproduce the state. So what is the result? The result is there exists some other state, which is a very good approximation to this state, such that you can prepare this other state in logarithmic depth. And the bigger the system becomes, in fact, this error of approximation becomes better. So that means in the thermodynamic limit, these states will be the same state. So they will have fidelity 1. Okay, so the error doesn't get worse, it gets better. In the thermodynamic limit is exact. That's why I won't consider the error from now on. I will just tell you how the circuit looks like. And now I just want to sketch the basic idea, which is you first spread entangled states, which is what is shown at the bottom, at distance which is logarithmic in the system size. And then it turns out you can explicitly read this type of circuit on top, which looks like a staircase, which is parallelizable. So at each chunk, it happens at the same time. And this is both necessary and sufficient. So this architecture is enough to produce all short range MPS. So every area law without long range entanglement. Yes.
So I don't understand this necessary implication, because if I take a product state,
Yes.
which is short range entangled,
Very good.
you cannot tell me that you need the logarithmic circuit.
That is true. So now, of course, we need to define the domain, right? So we need to know what states are we considering. That's why in the previous slide, the domain was short range correlated states. And that is a technical term, in fact. So you can define them very precisely using the language of MPS. I don't know if you're familiar with this language. It will be injective MPSs. But if not, it means states with exponentially decaying correlations. So this is what is missing. So what I'm claiming is if you have a state with exponentially decaying correlations, if you try to reproduce it with constant depth, you will fail. It is clear. So take AKLT.
Okay, but the product state still needs its exponential decay correlation with correlation length 0.
Yes, but my claim is you cannot reproduce this class with this type of
Okay.
So you cannot produce all short range correlated state. In fact, you cannot produce any of them, except product states with translation invariance. None of them. There doesn't exist a single translation invariant matrix product state which is not zero correlation length, so has some finite correlation length that you can reproduce.
So if you take an MPS with bond link 2,
yeah, that's
you need the logarithmic circuit.
Yes. And the key again is the tails. Exponential tails, you will fail reproducing them if you are constant depth. So that's why you need the logarithm. Okay, thank you for the question. Any more questions?
Maybe.
Yeah.
So why is it so important to reproduce correctly the tail?
Well, this is the task I have here. So I haven't specified, what you need this for. So that the nicest requirement you could have is to reproduce the state exactly, and that's what I'm doing.
Okay.
So I want to reproduce the state exactly, not up to local observables or up to errors. I want the state in all lengths with perfect fidelity, and that's what I'm doing.
Okay.
Of course, if you have a more specific application in mind, maybe you can cut this cost. But here I'm not doing this. I'm considering the most general setting, right? Okay. Good. Okay. So now we'll bring in the second ingredient, which is how you can do better than this. And the result I will analyze a little bit is now consider measurements and feedback, which means you're allowed to measure locally and then unitarily act based on the measurement outcome. Can you do better in the preparation? And now I will claim two results, which are both true, but they have different trade-offs. The first one is that now one round of measurement and logarithmic depth, you can do every matrix product state. So not only short range correlated like previously, but you can do long range correlated. That includes GHZ states. Okay, that's why you need the measurements. So measurements allow you to create long range entanglement. And the second is an improvement, at least theoretically speaking, which is you can do even better. You can do an exponentially better in time or in depth in this case, which is log of the system size. And that's sufficient. And let me show you, okay, sorry, before I show you two comments. So first comment is, although we're doing measurements, this is not post-selected, it's deterministic. And this is to be contrasted with many talks of the first days where they had a different setup. They were doing measurements and they were observing the system, but it was post-selected. This is not post-selected. The point here, you will always get your target state out. You just need to act accordingly, right? No matter what is the measurement outcome. So there's no post-selection. And okay, the second comment is this algorithm is an exponential improvement with respect to what was there before, including measurements. Okay, so how does it look like? I will skip kind of fast through this slide. You see that the architecture looks very similar. The difference is the bottom state is the like initial state you somehow prepared at first looks kind of different, and this is why you need the measurement. So you do again the same circuit at the top, but the bottom part looks different. And I'm not like telling you in detail how to do this, but it can always be done no matter what is your NPS. And to do the double log, to have a log, you need to do some kind of tree structure. Okay, so I won't go there in detail, but the claim is this type of circuit will work for every MPS. Okay, so this is, yeah?
I have a question. Where does the information about the bond dimension enters?
Okay, as I announced at the beginning, here I'm considering the task where bond dimension is anything but fixed and you increase the system size.
Yeah.
And this is,
I guess this large bond dimension should play a role in the prefactor of this bond.
exactly, but I'm looking at the scaling. It's only the prefactor. Here we have in mind the setting which is natural for tensor networks. You define the tensor and then you repeat it n times. And you want to know how the cost scales with n. And as you pointed out correctly, D, the bond dimension, will change prefactors, but it won't enter the scaling with n.
Because classically you can say that this with n, the cost is constant. Right?
With n, the cost is constant.
So if I want to put anything about a state that is not a state with fixed bond dimension, then a diagonal transfer matrix is some function of bond dimension, and I can.
But okay, the crucial difference is here, I'm not doing stuff in my classical computer. I'm using the classical computer to tell me what are the quantum gates I need to implement this on a quantum device.
Yeah, but it seems that the quantum device then is still worse than the classical one.
But in the classical, you're not preparing the state, right? In the classical device, you have your tensor, you're done. Now I want to create the states to use them for something else. So if I have a variational algorithm, okay, for MPS is not so useful because you can contract them in classical computers. But if you have PEPs, which maybe I will talk later if I have time, you know, that doesn't hold. You can't contract PEPs in a classical computer. You need to actually prepare the state on a quantum device. That's why this is relevant in my opinion. Okay. So, good. So what is left for at least one dimension? So there are two short comments I want to make. The first one is that this was for translation invariant states. There are non-translation invariant states, and pretty much the bottom line is the same thing works. And the reason the same thing works is if you generate random matrix product states, it turns out they're short range correlated. And we show this in this work, but this method is not original. This was known before even different settings. So the key point is because they're short range correlated due to randomness, you will the previous algorithm works. It's just inhomogeneous. It depends on the position, but the same architecture will create the same state with the same accuracy. Okay, and the second comment is slightly more technical. Thank you. Which is okay. There's something else left out, even with translation invariance. don't want to explain why now, but it turns out if you use matrix product states, there are some nasty states that are still translation invariant, but you cannot represent with the same tensor everywhere. And these nasty states are so-called W and Dickey states. So this one has to treat separately. And my only comment here is that this can be done. And there were first a work by Harry Berman and his group, where they showed log n ancillas are enough to prepare this W state, and then we improved on their scheme by simplifying it and showing that this can be done with even system size independent resources. So the take-home message from this slide is there are some other states not included in what I talked about, but this can be done separately. With using their structure, one can even do better. Good. So last few minutes, I want to just branch out on the rest of the works I want to talk about. So this is about using symmetry now. So where is symmetry? Where does symmetry come here? So if you think like condensed matter physicists, symmetries are very important if you want to classify phases of matter. And what I have been talking about, I brand it as preparing states, but you can also think of it as classifying phases of matter. And the reason is, if you understand what shallow circuits prepare, then you also understand phases of matter, because that's exactly the definition of a phase. A phase is whatever has the same long-range entanglement, but short-range you don't care. You just say it's in the same phase, and that's exactly what I have been studying here. So you start from a state, and you act with short-depth circuits, and you see what you get. So, for instance, one conclusion, phrased in different words, is that GHZ states are in a different phase than the product state, exactly because you cannot prepare it with a shallow depth circuit. However, notice that using measurements, this phase diagram collapses. So my point here would be that one can classify phases using symmetries, and it was done, maybe you know about this. The classification is given in the so-called homology classes. So what we did was to consider now both symmetries and measurements together and classify phases of matter. And we do this, I haven't told you in detail or what is the setup even concretely, but taking my word for it, the result is that now if you look at matrix product states that are protected by symmetry, then using measurements is still beneficial. So the phase diagram will collapse even in the presence of symmetries, and we show this for a billion groups and this other class called 2 nilpotent groups, which I won't define now. But the important part, the take-home message, is that the phase diagram changes of classifying phases of matter, even by including symmetries. So measurements give a non-trivial freedom. Okay, I don't have time to go through the last part. Let me just say the take-home message from these 2 slides. So now the task is to understand what happens in 2 dimensions, which is the really interesting things, but here is far harder to understand what is going on. So we focus on the subclass of PEPs, which we can prepare in constant depth. And my claim is that this class can be defined by using some ideas coming from matrix product states, and is what is shown here in this diagram. So the idea is that if you impose a symmetry on the PEPs, then this symmetry will allow its preparability. And this symmetry is, okay, roughly speaking, is that some Pauli operators from the bond leg slide on other bond legs. So I don't have time to tell you in detail, but the take-home message is that we identify some kind of symmetry where using measurements and feedback, one can prepare the states deterministically. And this includes many interesting examples like topological states, like the Tori code and so on. And we analyze all these things, but I don't have time to tell you about it. Okay, with that, I think I should wrap up. So let me say a few words on the outlook. First, summarize. So I have talked about preparing states on quantum devices. And the first thing was that having short-range correlated states, logarithmic depth is both necessary and sufficient. From the view of complexity theory, that settles the exact complexity of these states, which is logarithmic. And of course, settles the exact complexity also of all matrix product states, because long-range correlated, as I said, is very trivial to know their complexity is linear. Good. So now I showed you how using a new ingredient can really help the efficiency of these algorithms. And this ingredient was using measurements and feedback exactly in the same way is done in quantum teleportation. So in fact, this ingredient leads to doubly exponential speedup in the sense that from linear, which is the worst case, now you can bring it down to double logarithmic in the system size. So there is yet a different perspective, more coming from the quantum information to understand this measurements and feedback picture, which is if you come from quantum information, you're very familiar with local operations and classical communication. This is exactly the generalization of quantum teleportation. And now what we're doing here, yet in other words, is we enhance LOCC, this class, with shallow circuits. And this, in my opinion, is very meaningful because if you don't do this, trying to classify LOCC classes has proven very unfruitful in the past decades. In fact, it was shown that there are so many classes that no state is connected to no other state, like it's measure zero, what you can reach without using shallow circuits. Instead here, using shallow circuits, which is very reasonable from a practical perspective, we show you can create all area law states in 1D. Okay, then I skimmed through very fast, but there's an implication for many-body theory. You can talk about topological states and how you can create these topological states and using measurements, and that connects to error correction very nicely because topological states are good error correcting codes, you know, from Tori code. And then, okay, this again the part that touched very briefly, that one can do a classification of phases of matter using both symmetries and measurements. And lastly, my last comment is that these ideas of using measurement and feedback is not only a theorist's dream, it has been realized in the lab. And here I quote just some experiments that use these ideas to create states experimentally. Thank you very much.
Thank you. Questions?
What is the class of text that can be made with measurement?
Okay, I can show you the picture and go through in somewhat more detail. Is the class that has the following symmetry. So let's say for simplicity, PA here is the Pauli, A is your tensor, and this UPA is some unitary. And what we demand is that the tensor has a symmetry which looks like almost symmetry protect topological phases, but not quite. Which is for every Pauli coming from the left leg, there exist two other Paulis, you see, which is on the right side. Such that only acting on the physical leg unitarily, you can get this identity. So bringing these two Paulis on the left side, you realize that's a symmetry condition. You act on the tensor and the domain is invariant. Okay, you can define this. I don't have time to show you now why that leads to preparability, but it does. It's very simple. But then now the really interesting question is, okay, what states satisfy this? Okay, and then we were convinced this has to do with topological states. So we found an explicit family, which is topological, and we show this, that has a symmetry. The simplest example is Tori code. You take the Tori code, has the symmetry for Pauli matrices. But it's not only a billion topological order that has this, so it's richer. And maybe a second comment to make is that this is a continuous, so you can have continuous families of tensors that have this. So this means you can prepare all of them in constant depth and jump phases. So you see, I found this slightly surprising. So you don't need linear depth or more resources, you just need measurements. And you can create continuous paths in the space of PEPs deterministically, which include trivial and topological states. Hopefully that gives you some sense.
Marco has a question.
The linear depth is usually in the unitary case related to Lieb-Robinson.
Sorry, can you say it again?
This linear depth is usually related to Lieb-Robinson in unitary case.
Exactly. So that's
with measurements in non-unitary dynamics, not so clear. Can you say something?
yes.
How many measurements do you need?
That's a very good. Okay, well, all these are very good questions. So let me just rephrase your first comment. So is indeed true that the reason one gets lower bounds for topological states, which are linear, is Lieb-Robinson bounds. So you can't create any topological state with less than linear depth just because of Lieb-Robinson. It's the same with GHZ states. So now, how come measurements go to constant depth and how many rounds? So in what I showed, including this, which has the Tori code, one round of measurements everywhere parallelizable is enough. So you do like you measure linear ON sites, but all at once. Okay, and okay, how can now this counteract the Lieb-Robinson? Is because the correction step, which is a local unitary, depends on the classical outcomes of everywhere in the system. So there is a classical information part, which violates the light cone. But if you think about it from a practical perspective, that's very simple. In lab, when you make measurements, of course, you know what the measurement outcome is everywhere. It is not the different galaxies where your qubits lie there in the lab. So it's classical communication that breaks the light cone.
Thank you.
There is, look at it, should
Okay.
definitely.
Is there a relation between this class and the isometric class?
Okay, that's another good question. In 1D, so you can have this condition in 1D, and you can show they are isometric peps. That also holds for 2D with a specific direction, but this class doesn't span isometric peps. So it's a subclass of isometric peps. Yes.
But
Indeed.
also isometric types can be better.
Well, easily you have to define it. They need linear depth.
Yeah.
For me, linear depth is bad because I have in mind Niski. You have a Niski mindset. If you go to a lab and there's a Tory code with linear depth, that's very hard. Noise will kill you. Okay, here is constant depth. One round of measurement, one round of correction, you're done.
Right. Thanks again, Georgios.
Thank you.